Good morning. Here we are again. I'm going to learn about electric fields due to continuous charge distributions. Again, I'm at home, and so you're probably going to hear the cat toy. You're going to hear my kids doing some science experiments. Lena and Jonah are over here. They're looking through the microscope, looking at flour and sugar and doing all sorts of fun sciencey things.
Hello.
That was Jonah saying hi. Um, so at this point, you were asked to do this worksheet. So you're asked to draw the electric field due to each of those circled charges. So it might have looked, your drawing might have looked something like this. So this one would be for this particular charge, or that charge right here. I feel like that direction isn't quite right. Maybe something like that. And then we'll do another one. And each one of those is going to contribute. Each one of these charges is going to contribute to the electric field. So that one might look something like this. This one might look something like this. You get the picture. And let's do another one down here on the bottom on the other side so that you can see what that one looks like as well. So maybe I'll do this one. And notice it has some symmetry to this first one that we drew, right? So they're the same size since they're equidistant from the half arc of charge.
And please do what you were supposed to.
Again, that was Jonah. You can see that they're equidistant from each of those charges and that they're the same size, right? Since they're the same distance, and we know the electric field due to a point charge, right? We're pretending each of those little circles are like a point charge. But I'm having you do this so that you can see kind of the progression from looking at just singular point charges to something called a continuous charge. So an charged object that's on a solid body where the charge distribution is continuous. So there's lots of charge on this solid object. And so you probably have gotten a hint of this already when Caden asked a question in class on Monday about parallel plate capacitors. Well, how do you know what the electric field looks like at that point? And I was drawing different charges on the parallel plates, and you have to add up all the charges or all the electric field contributions to each of those charges. That should start ringing a bell to you. You should be hearing integral calculus, right? That's what we're going to be doing this morning, is figuring this out. So I'm actually going to make two different videos today. One is going to walk us through one example, and then the second is going to be a different example. And so you can look at them at two different times. So we are responsible for specific charge distributions. We're not responsible for every single one in the entire universe, but we're responsible for specific ones. So these are the ones that we are responsible for. So one of them is if we have a ring of charge, we can, or we should be able to, by the time we're finished, find the electric field at any point along that central axis, that is the central z-axis. If we have a line of charge, we should be able to find the electric field at this point P here, also this point P here, or this point P anywhere along at some distance from that charge line. Also, we have a disk of charge here, so we should be able to find the electric field at this point due to that disk of charge, which there's going to be a lot of similarities between this ring of charge and this disk of charge, if that makes any sense to you. And then similar to the ring of charge, we also will be able to find the electric field of an arc of charge, but notice that we are not along the z-axis on that one. We're just flat in the same plane as that arc of charge. And this is actually the one that we're going to spend time looking at this morning. And then our second example, I believe, is going to be one that looks like this right here. So we're going to start with this one. So let's just take kind of a minute and look at that. You're going to see that you have a arc of charge, and they have broken it down, and we're going to look at this picture in a whole lot more detail. So I'm going to ask you to pause the video at this point right now, and I'm going to ask you to draw this picture in detail. Okay, so take a moment and draw that picture in. All right, I'm going to try to make this video as fast as I can, knowing that you can stop and rewind. So I'm going to probably talk a little faster than I would in a normal class period, but you can go back and listen to it. I just don't want this video to be a half an hour long, which it may end up being. Okay, so our goal here is to find the electric field at some point P on a central axis, and we're going to, remember, find it at this point P here. Right, that's our goal for today for this specific example. but first, before we do that, we need to have some background information. This table is in your textbook, and it is super important. You will want to pay attention to it. You are going to want to know these different Greek symbols and what they mean. So the first thing that we need to know is that we're confined a little bit on our work. We have to make sure that the charge distributions that we're dealing with are uniform, meaning that charge is uniform over all of the objects. So we saw that arc before, that means the charge is evenly distributed. And the total charge Q on the object can be expressed as a charge density, right? So this is a lot like a mass density, and you can either do that times length, surface area, or volume. And then we're going to break down those continuous charges into little teeny bits. We'll break down the continuous charge into little discrete parts. We'll call them dq, like a differential, like a little bitty charge q. So if we take a look over here, charges in Q, and then our symbol for charge is Q, and then our SI unit is Coulomb, right? A linear charge density, which is what we are going to use for that arc of charge, because that's like a line of charge. We have our lambda here, that's our symbol for it, and that's coulombs per meter. Then we also have a surface charge density. So if you think back to that disk that we were looking at, this disk here, this would have a surface charge density. This would have a linear charge density, linear charge density, linear charge density, and then here again, this would have a linear charge density. And then the other, so that is sigma. That little guy right there is sigma. And then a volume charge density is rho, and we've seen rho before. We're not going to deal a lot with volume charge density at this point, but it behaves the same way as our linear and our surface charge density. Okay, so overview, we're going to break down our continuous charge into discrete little parts. All right, those are called our dq. So since our charge is uniform, if we look at any example, if I just were to take and look at a little teeny bit right here, this little teeny bit of this ring or this arc, you can think of it either way. That little bitty part right here is going to have a little charge. We call that little charge dq. Right? That's the little charge. The charge on the whole thing is Q. You with me? And the small arc length that encloses or encapsulates dq is called ds. So that's like the little arc length. Instead of the whole arc length of s, it's a little arc length. And because the linear charge density is constant, right, is uniform, we can say the dq, the little charge bit over the little arc, is the same as, and this should be little q, I apologize, that's confusing. So we got our charge, our total charge that's on our arc divided by our total length. Those are both equivalent to our linear charge density. Hopefully that makes some sense. Okay, so let's take a look at our example that we're going to be looking at. Our job is to just derive an expression. So we're going to be deriving an equation for the electric field at point P for the figure shown. So point P is right here, right? And you can see that they've kind of started to go through drawing some of those. So if you have not taken a detailed drawing of what's on your screen right now, pause the video and detail draw it, because you will want this to refer back to over and over and over and over and over again. Notice a couple things, that this charge actually has this rod actually has a negative charge Q. All right, and they've drawn some electric field contributions from, here's our little ds, our little arc length that has a charge dq, right? And they've drawn the electric field from our point here, and it points toward our arc because the arc is negatively charged. You with me? I hope. Okay. So let's kind of keep going down here. So our general method is to pick a small chunk of charge. That's what we call dq, and it's located on a segment ds on the arc, or dx on the line. So again, we're going to break down our continuous charge into a small bit ds that houses the charge dq. We're going to find the electric field for that little chunk. That's called dE. That's the little electric field. So you can see that up here. You see that this right here is our small arc length that houses dq, like the little bitty charge. And then here is the electric field that is due to just this small piece, and we call that dE. It's not the whole electric field, it's just the little bit of the electric field. And then once we have that set up, we have that expression, we're going to integrate over the whole line of charge to find the net electric field, right? If you think about net means adding up, right? We're going to find the net electric field at that point, at point P, due to the entire charge, okay? So what I'm going to do is the next couple of screens are going to have a tactic and then the example, like how to do the tactic. And so what you're going to want to do is you are going to want to look at the tactic as this is how what I'm going to do in every situation where I'm asked to find one of these electric fields. And then the in practice is going to be when you are how you apply it to that particular situation. The in practice might look different in different situations, but the tactics will remain constant for every problem that you're going to be looking at. Okay, so let's get started. Again, we're going to be looking at this situation. All right, so our first tactic is we need to relate our charge element dq to our length element. And in this case, our length element is ds. If you think back a couple slides ago, we do that through a linear charge density, right? A linear charge density. So this is true, right? dq, that little charge, is going to be equal to the linear charge density times that little charge length, right? This guy right here, our little charge length. Okay, so there's our first bit, our first tactic. Our second tactic is to express the magnitude of the electric field at point P that's caused by that little charge, right? So we're basically going to treat this little piece right here as a point charge, right? And we found the electric field for a point charge already, right? We did that in our simulation. So here we go. You ready? So our electric field is equal to K times our charge. But remember, it's not the whole charge of the whole arc. It's just the little bitty charge, right? It's the little thing of charge over R squared, right? That's our formula for R squared. Now, what we're going to do, though, is we're actually going to take this, and you're going to see why in a little bit, but we're going to take our dq and we're going to replace it with this. So we're going to take this right here. We're going to take this and we're going to put it right here, right there, okay? So now we have this expression, right? So we have our little electric field, our bit of electric field that's caused by that little bit of charge is going to be equal to our Coulomb's constant, our K value, right? Times our, again, our linear charge density is also a constant value, and that's going to be ds over R squared. Okay, so there's our first one, our first two tactics. Now, this isn't as simple as being able to just add this up. We can't integrate at this point because we got to go back and look up here. If we look at each of those contributions to the electric field, only part of the electric field, the x component, is going to contribute to the net, right? Because we have this symmetry, we have this equal one over here, that those two y components are going to cancel out. Like this y component cancels with this y component. While it's there, they add up to be 0. So we're going to look for some symmetry to see if we can do some simplification. So here we go. Here's our symmetry. So we're going to look for symmetry and we're going to cancel anything out that's possible. So we realize that our electric field, only the x components of each of those electric fields are going to contribute to our net electric field. So we rewrite our electric field like this, our dE times our cosine of our angle, right? That makes sense. Here's our angle here. Yes? Nod? Yes? Okay. And then only the x direction. So that's why we use the cosine. All right, so then we rewrite, right? We rewrite, and once we rewrite, we take our electric field expression from our last slide, K times our lambda, which is our linear charge density over R squared, and then we have times a cosine of theta ds. Now, if you're starting to think ahead, like, hey, Mrs. T, we're going to have to integrate these, we know that these two variables have to match, right? Our variable here, because let's think about it for a moment. This is a constant value, right? K is a constant value. So is our linear charge density. That is also a constant value. And then this is also constant. That doesn't vary. Now, this is where it will vary sometimes between problem and problem. Sometimes the distance does vary. But in this case, since we're looking at a circular arc, right, and we're looking at the central point P, that actually stays constant. Okay, so this is a constant. So these values all right in here are all constant. It's just this guy, that's the variable. So we'll go from one angle to another angle. So from a negative 60 degrees up to a positive 60 degrees. All right. So we got a problem. These two things are not matching, and we need them to match. So we come over to this idea here. Remember that our arc length is equal to our radius times our angle, right? That's just a definition of an arc length. You with me, you with me, you with me? I hope. Okay. So we can also say that ds is equal to r times our d theta. So I hope that you're seeing now that if I were to take this and substitute it in for our ds, then our variables would match. You with me? I hope so. Okay. So when I substitute in my idea that my little arc length is equal to my radius times my little theta here, and if you come back up here, you can see that maybe a little bit better, right? So this d theta is just that little bitty teeny arc there, and then our ds is that little bitty teeny length, right? And so that ratio will be the same for the arc length or the small arc length, okay? So then we substitute in for ds. Right here, we substitute in r times d theta so that we get this variable to match this variable. And when we do that, we can do a little canceling out. Notice one of our radii cancels out. And hey, here's our expression, and we are ready to add this up. We are now ready to integrate. I forgot a theta in there. That's confusing. Let's make sure that we have that theta in there so that we're not confused. So this is theta right in here. You with me? Okay, so we've got our little electric field contribution, k times lambda over r, those are all constants, right? Times the cosine of theta d theta. And notice this variable matches this variable, so we can actually integrate it. All right, now we're ready. Yay, now we're ready to do the math. We've done the physics, now it's time to do the math. Okay, so our next step is going to be to integrate, and we're going to integrate to find the electric field. We need to use limits of integration that's given up by the situation. So you have to look back at your picture. So if you look back at your picture, we know that we go from this negative 60 degrees down here up to this positive 60 degrees. Those are going to be our limits of integration. Hopefully that makes some sense to us. In speak, if maybe this makes sense to you, you're going to add up all the DEs, the little electric field bits, contributed by all of the DQs. We're going to add all of those up. And we're going to do that through integration. Okay, so here we go. So we're going to integrate. And so this side will just become our net electric field. Okay. Notice I pulled out k, lambda, and r. Those were all constants in this situation. If you don't remember, go back and listen because I explained that earlier. And then notice our limits of integration are going to be negative 60 to a positive 60 degrees, which is again given by the situation. Integral of our cosine function is just going to be our sine function, and then we're going to evaluate that from negative 60 degrees to a positive 60 degrees. And so when we do that, our 60 degrees here, our sine of 60 degrees is the square root of 3 over 2. And then our negative 60 degrees is a negative square root of 3 out of 62. What am I saying? Negative square root of 3 over 2, right? So then we get a, and this is a little hard to see because I've got it written in multiple places, but this is square root of 3 over 2 minus a negative square root of 3 over 2 gives us our expression for our electric field. Woo! Yay! We did it, right? So we've got our expression for our electric field, which is k, and then lambda, and then we've got the square root of 3 over r. Okay? Big sigh. We are almost done. I know you thought we were done, but we were almost done. Not quite. If we think back, we really need to be writing this in terms of our original charge, not our charge density. So we just need to basically substitute back in for our charge density so that we get our electric field in terms of Q instead of lambda, okay, instead of our charge density. Okay, so here's our next tactic. Our next tactic is we want to keep it positive. We're going to discard the minus sign. We're just looking for magnitude. Your picture draws your sign. In this case, we didn't have a negative, so we didn't need to worry about it, right? Okay. And so we, again, want to rewrite our electric field in terms of Q and not lambda. So let's do that. So if we're going to write lambda in terms of R and Q, what we would do is, if I think about that, isn't it a third of a circle? Like negative 60 to positive 60 is a third of a circle. That's 120 degrees. So that's a third of 360 degrees. So we know our arc, our charge density is going to be our charge per length, right? So our arc length in this case is 2 pi r, and then that's divided by 3 because it's a third of the arc length. You with me? Okay, and so then I just kind of rearrange that. I just flip that 3 up onto the top, and I'm going to take this, and I'm just going to substitute it back in for lambda. And remember, the purpose of that is just to write our electric field in terms of Q instead of lambda, okay? So that's where it says here, replace your charge density, either our lambda or sigma, with total charge in the object per length, okay? So then when we did that, we get our expression, and we are actually done at this point. So this is actually our I don't know if this will work. This is our electric field, right? This is our electric field for our, I don't know what just happened. This is our electric field for this charge distribution that is shown here. Woo! Okay, so what we're going to do is I am going to stop this video now. I'm actually going to go check on my kiddos, and then I'm going to make another one so that you can see how to do all of these tactics in another situation. And I'm going to ask you to go and stop and go and stop and go and stop. So we'll kind of go back and forth that way so you see this more than one time. All right, thanks for following along with me this morning. Send me a message if you have any questions.